Good evening, everyone. We are team number 12 and our project title Lean Attention Hardware Our Scalable Attention for Transformers Decoding. This project falls under the reproducibility challenge track. We aim to implement and validate the claims of the Lean Attention paper, specifically targeting the inefficient found in large language models inference on modern GPU like the NVIDIA A100. My team members are uh, Sravanthi, Vishesh, Mahi, and myself. So let's look into the core idea of our project, the bottleneck. Um, the bottleneck decode phase. To understand our project, we first need to look at the core problem, the decode bottleneck. In transformer inference, we have two phases. The prefill phase, where we process the prompt in compute bound and very efficient because we are doing large matrix multiplications. However, the decode phase, generating text one token at a time, is memory bound. The real issue arises from how we parallelize this work. Standard mechanism like flash attention, uh, batch size, and number of heads. But in real world scenario, the batch size is often very small. Like it's sometimes it's just one. So if you look at that, an NVIDIA A100 GPU, it has 108 streaming multiprocessor SMS. If our model has only 32 heads and standard attention uses only 32 streaming multiprocessors, that means 76 streaming multiprocessor sitting idle and doing nothing. So this is known as the tail effect, and it is a massive waste of hardware resources. Uh, let's look into project objective and its approaches. This brings us to our project, our objective. Our goal was to reproduce lean attention to fix this utilization gap. The core idea is stream K decomposition. Instead of assigning work based on heads, which is a fixed logical dimension, we split um, we split the physical sequence length itself by breaking the key value cache into lean tiles. We can distribute the decoding work across all 108 streaming multiprocessors regardless of the batch size. Our target for this project was to implement this kernel and demonstrate a 1.7x to 2.5x speed up on long context sequences, verifying that hardware aware partitioning is the key to scalable inferences.
Thanks, Anjali. Now that we understand why the tail effect hurts performance, I'll explain how our implementation solves it using our split KV architecture. In traditional attention implementation, there is a split rule. One attention head equals one thread block. This means if you have a batch size of 1 and 32 heads, you can only launch 32 blocks of work. On a A100 GPU with 108 streaming multiprocessors, this leaves 76 streaming multiprocessors completely idle. So our approach lean attention changes this mapping. So first we decouple the work from the head dimension and instead split the sequence length itself. We treat the key value cache as a large pool of data. Then we slice this sequence into fixed chunks called lean tiles specifically. We used a tile size of 128 tokens. So for a sequence of 32,000 tokens, we generate roughly 250 tiles per head. This effectively explodes the amount of parallelism available, allowing us to flood all 108 SMs with work, regardless of how small the batch size is. To achieve this, we built a two-stage kernel pipeline. The first one is the mapper kernel, which computes partial attention scores for each tile, and the second one is the reducer kernel, which aggregates these partial scores into the final output. So let's dive into phase 1, which is the mapper kernel. So this is where all the heavy computation happens. Here each thread block on the GPU is assigned one lean tile, a specific chunk of the key and value matrices. So in total this process has 3 steps. The first one is load, where we load the single query token into shared memory. Since the query is the same for every token in the sequence, loading it loading it once into the fast memory saves massive bandwidth. And the second step here is the compute. So, so we stream these keys and value from the global memory and perform a dot product, that is q dot k transpose. And the third and most critically, the online softmax. So this is the hardest challenge in splitting the sequence. So whereas standard softmax requires you to sum all the exponentials of the tokens to normalize the probability, but here inside the kernel we only see one tile, we don't know the global sum. To solve this, we use the online softmax trick. Instead of calculating the final probability, we track two local statistics in the registers. The one is local maximum and another is the local running sum of exponentials, that is I. We update this iteratively as we stream data. At the end of phase 1, we don't write the final output here itself. We write the partial output along with this local m and the sum of exponentials I. Statistics back to the global memory. So this brings us to the phase 2, the reducer kernel. So at this stage, we have hundreds of partial outputs which are scattered across the GPU memory. We can't simply add them up and each tile was normalized by a different local maximum. So it would be like trying to add fractions with different denominators. So the reducer kernel here fixes this using a mathematical reweighting strategy called final global max. The kernel first reads all the local maximum from all tiles and then identify the true global maximum m global for the entire sequence. Then comes reweight. It then calculates a correction factor for each tile. If a tile has a had a low local score, its contribution is scaled down exponentially based on the difference between the local max and the global max. And then comes the final step, aggregate. So here we finally compute the weighted sum of the partial outputs. This formula you see on the screen ensures that our split up computation mathematically converges to the exact same result as a standard attention. This allows us to massive parallelism without sacrificing numerical accuracy. So now we have seen phase 1 and phase 2 of kernel logic. Now Ramya will explain how we integrated this C++ code into PyTorch.
To walk you through the implementation stack we used to build this ecosystem. We couldn't just write a standard C++ file. The model needed to fit smoothly into the deep learning ecosystem. So we developed the system using PyTorch C++ extensions, which allowed us to call our custom CUDA kernels directly from Python. We ran everything on NVIDIA hardware, and our software stack included PyTorch 2.1 and CUDA 11.8. This combination gave us both high compute performance and compatibility with the latest deep learning features. Now let us see our system components. Our system is structured into three layers. The first layer is the Python layer frontend. This is where we prepare data and trigger benchmarking. And the second layer is the Py911 interface. This layer bridges the Python and C++ worlds. And the third layer is the CUDA backend. This is where the heavy computation happens. We wrote custom C++ and CUDA kernels, and to optimize matrix operations, we used NVIDIA Class 2 templates. These templates helped us to get better performance without handwriting every low-level instruction. We also integrated NVML, and which allowed us to read GPU power consumption programmatically. So we could correlate performance with energy usage. And here are the profiling tools. For performance analysis, we used NVIDIA Insight. This helped us to inspect wrap occupancy and pipeline stalls. Inside our kernels, we could fine-tune the GPU execution. And the next is the NVML. This gave us power draw measurements at millisecond level precision. Python for usability, Py9 for bridging, and optimized CUDA kernels for raw performance, all supported by strong profiling tools. Now, Let me briefly explain why we used NVIDIA CutClass in our ecosystem, in our system. CutClass is a template library that provides high-performance building blocks for GEMM, which is the core operation in most deep learning models. Instead of writing everything manually in CUDA, CutClass gives us optimized structures that already match the GPU's architecture. We use three key optimizations for CutClass. First is the vector loads. Using instructions like we can load 4 FP16 values in a single operation. This maximizes memory bandwidth and significantly speeds up data movement. Second is the wrap away primitives. Instructions like let threads within a wrap exchange data without using shared memory. This reduces latency. And third, we customized the CutClass figlobe functor. This allowed us to fuse our online softmax update directly after matrix multiply instead of launching a separate kernel. In short, CutClass gives us both speed and flexibility, letting us build a kernel that was highly optimized while still being easy to extend for our use case. While building the system, we have faced three major engineering challenges. Now let us see our challenges. The first challenge was float point instability. Using FP16 for building this ecosystem, we faced three main engineering challenges. One first challenge was floating point stability. Using FP16 for exponent accumulation caused underflows and nonce for long sequence. To solve this, we switched to mixed precision. And the second challenge was grid level synchronization. Our reducer kernel sometimes launched before all mapper blocks had finished writing their outputs, which created inconsistent results. We fixed this by adding an explicit QRAF string synchronized barrier between phase 1 and phase 2. And the third challenge was occupancy tuning. Initially, high register pressure restricted us to only one wrap per block, which limited throughput. We tuned the 3 block size, increasing it from 128 to 256, so GPU could hide memory latency more efficiently. So, in summary, by addressing numerical stability, synchronization, and occupancy tuning, we were able to make the kernel both correct and high performance.
Thank you, Ramya. Now, to validate the effectiveness of our lean attention implementation, we moved to the experimental evaluation phase. We didn't just want to run code, we want to simulate the exact conditions where modern LLMs struggle the most. If we first let's talk about the hardware. We ran all our experiments on a single NVIDIA A180 GPU. We specifically chose the A100 because it is the industry standard for LLM interference today. So, like crucially, it has like 108 streaming multiprocessors. Remember, like our whole hypothesis is that standard attention leaves most of these SMS ideal. So, like by using this high-end GPU, we can truly test if our split KV method can saturate such a massive chip compared to the baseline. So next the test matrix, we focused on the three variables, batch size and head dimension and the sequence length. If we see the batch size of 1, we kept the batch size fixed at 1. This is like critical. So in the training, you have a huge batch size, but in real world interference, like when like you are chatting with a bot, the batch size is often just 1. This is the decode phase, which is memory bandwidth bound. This is the hardest scenario for a GPU to handle efficiently. So and also like this is exactly where we wanted to test our solution. And if we see the head dimension 128, this is standard for models like LLAMA and GPT. And the sequence length, we push the context from 2000 tokens all the way to like 32,000 tokens. We push 32,000 because the industry is moving toward long context models analyzing entire books or massive PDFs. So this is where the tail effect usually destroys performance. So we need to see how lean attention holds up under this pressure. So like finally our baselines, like we compared our kernel against the standard PyTorch scale dot product attention, which utilizes the highly optimized flash attention backend. So effectively we are comparing our student implementation against the current state of the art. And if we go into the next slide. Moving on to our latency results, this graph tells the story of our project. On the x-axis, you see the sequence lengths increasing from 2K to 32K. On the y-axis, the latency, so lower is the better. So the short context 2K to 4K, if you look at the left side of the graph, you will see that the short sequence, the performance of lean attention and the baseline is roughly comparable. In fact, we sometimes see a slight overhead about 5 to 10% slower. So this is expected behavior. Lean attention splits the calculation into two separate kernels and requires synchronization between them. So for short sequence, the work is so light that the cost of launching these kernels slightly outweighs the benefits of the parallelization. We call this kernel launch overhead. So the long context, if we see, which is like greater than 16K, the hockey stick effect. But as we move to the right side of the graph, past 16 tokens, the behavior changes dramatically. Look at the red line. It starts shooting up like linearly. This is the tail effect we discussed earlier. So the baseline is assigning one attention head to one thread block. So with only 32 heads, it can only use 32 SMS. So the other SMs on the A100 are sitting ideal. So like wasting time while the active ones struggle with the massive workload. So the lean advantage is like now look at our like blue line, lean attention. It significantly flattens the curve. So like basically we decouple the work from the number of heads. We are able to take those 32K tokens, split them into small tiles and distribute them across all 108 SMs. So the key finding is the context length of the 32,000 tokens. The baseline took roughly 98 ms, while our lean attention finished in just 40 to 46 ms. So this gives us a 2.1x speed up if we see. So to put that in the perspective for a user, this means the model generates text twice as fast. So we have to like we have successfully converted the ideal like silicon of the GPU into useful work, proving our hypothesis that hardware aware partitioning is the key to scaling interference. So next part will be continued by the Nandini.
Hello everyone. So now I'll be explaining one of the interesting findings in our work relates to energy consumption. There is a well-known concept in hardware architecture called race to array. This idea is that if a kernel can use more compute resources and finish to an idle or low power state sooner. So even if instantaneous power draw is higher, the total energy consumed can actually be lower. In our case, that's exactly what we observed, and although our attention kernel triggers more SM activity on the GPU and momentarily increases peak power, it also finishes the computation much faster. Because of the 2.1 times speedup, the total time spent per batch is drastically reduced. And as a direct result, we measured a 45% reduction in total energy consumption per batch. This is a very meaningful result, especially when we think about real-world deployment of large language models. At scale, energy costs are one of the biggest bottlenecks, not just performance. So achieving faster inference and lower energy consumption is a major step towards sustainable LLM deployment. So moving on to statistical verification, which is arguably the most critical part of the entire project. The principle here is simple: speed is valuable, but correctness is non-negotiable. If an optimized kernel produces inaccurate or unstable results, it doesn't matter how fast it runs. So before making any claims about performance, we rigorously verified that our implementation computes the same results as standard arrangements. Coming to methodology, to validate correctness, we followed a structured testing pipeline. And we generated random Q, K, and V tensors using a Gaussian distribution, which is standard practicing in deep learning benchmarking. So this ensures we are not tuning or validating on cherry peak inputs. We computed the ground truth output using PyTorch, standard torch. Matmul in FP32 precision with source as the numerical references. We then compared our optimized implementation directly against this FP32 baseline across thousands of random samples. And coming to validation metrics, we evaluated accuracy using two complementary metrics. One is maximum absolute error, that is the largest difference across all elements between our kernel's output and the FP32 baseline was less than 183. For FP16 computation, this is well within the expected tolerance. And the another one is Frobenius norm of the difference. This checks similarity across the entire tensors, not just the max element. The Frobenius values confirm that our outputs match extremely closely with the reference. Together, these results confirm that our implementation is numerically stable, precise, and fully aligned with the mathematical definition of attention. And verification conclusion. Based on the statistical validation, we conclude that our implementation is mathematically equivalent to standard tension, and despite the performance improvements, we did not introduce any approximation, instability, or deviation in correctness. This means our speedup is truly a drop-in replacement for standard attention without compromising accuracy. So, to conclude the presentation, we successfully reproduced the lean attention mechanism using stream K decomposition. We rigorously validated the numerical correctness through statistical verification. On NVIDIA A100 hardware, we achieved a 2.1 times speedup and a 45% reduction in total energy consumption. And finally, our next step is to extend this implementation to support batching, which allows serving multiple users with different sequence lengths efficiently, something extremely useful in production LLM systems. So that's all we wanted to present, and thank you for your time.